Hello students, I'm Dr. Aisha Siddekha, Assistant Professor, Government First Grade College, Tumkur. In the present session, we are going to talk about variation of radial and angular parts of the hydrogen wave functions for different orbitals 1s, 2s, 2p, 3s, 3p and 3d orbitals. We're going to learn only about the graphical representation of this. In the previous session, we have seen how Schrodinger wave equation can be applied to a system like hydrogen atom up to particle system. We also learned how there is a change into the polar coordinates from the Cartesian coordinates, and we also learned the equation given in polar coordinates. When we define an orbital is defined as the three-dimensional space around the nucleus of an atom where probability of finding an electron is maximum. So it is in the range of 90 to 95%. A large number of orbitals are possible in any atom as the number of atomic number goes on increasing. The possibilities of different orbitals is possible. Qualitatively, these orbitals can be distinguished by their size, shape and orientation. Different size, shapes like spherical, dumbbell, all these are there. Smaller the size of the orbital, more is the chance of finding the electron near the nucleus. I think this is quite clear. If the orbital is very small, it will be the electron will be quite close to the nucleus. So as the size goes on increasing, as the atomic number goes on increasing, it is quite possible that the electron may be moving away from the nucleus. The shape and orientation mean that there is more probability of finding the electron along certain directions only. So this gives directional properties to the orbitals. Now let us come back to the different parts as we have seen in case of Schrodinger wave equation, which is applied to the hydrogen atom. We have the in terms of polar coordinates. When we solve this equation, we are going to get an expression in terms of spherical coordinates. So x, y, z are known as the Cartesian coordinates. The r, theta and phi are known as either the spherical coordinates or otherwise also known as the polar coordinates. Where r is the distance from the center of the nucleus, phi is the angle to the positive z axis and phi is the angle to the positive x axis. So we have, this is the equation which we arrived at in the end in the previous video. So it has been written in a different form also. So psi of r, or r of the polar coordinates is equal to r of r, which is known as the radial function. And we have the angular functions which consist of theta and phi. And this is independent of the theta and phi. So it is the product of two functions. Now let us come to the radial probability density. The square of the radial wave function for an orbital gives the radial probability density of finding the electron at a point at a distance of r per unit volume. Now, how do we define radial probability? It is the total probability of finding an electron in a three-dimensional region around the nucleus when we consider two spheres having the radius r and r plus dr, where dr is the infinitesimally small distance. Now consider this, we have a small sphere here of the radius r and there is one more sphere which is having the radius of r plus dr, and this dr is very small, infinitesimally small. Now radial probability is given by 4 pi r square into dr. Now whatever volume is covered under this region is otherwise also known as radial function. So now we can define that radial probability, it is the product of radial function and probability, that is psi square. Therefore radial probability r is equal to 4 pi r square dr into psi square. When we plot this psi and psi square against r, that is the distance or the radius, we are going to get different graphs like this for different orbitals 1s, 2s, 3s, 2p, etc. Now if you try to analyze this for 1s orbital, which will be spherical in shape, as the distance goes on increasing, the probability of finding the electron also goes on decreasing. So it is very close to the nucleus here. But when you come to the 2s orbital, initially it will be near the nucleus, and as the distance goes on increasing, even finding the probability also goes on becoming lesser. So we can say that this is closer to the nucleus. In case of 1s, electron will be lying more close to the nucleus. So likewise, we can always go on and analyze all these plots here. This is plots of r psi. We can even replace this r by psi in different dimensions. Now let us come to the radial and angular nodes and their significance. What is a node? It is a point where finding the wave function is 0, or finding the probability of finding the electron is very much less, or literally equal to 0. Most of the time the intermediate region, a spherical shell where the probability is 0, is known as nodal surface or node. Now see here, in case of 1s orbital there are no nodes. But when you consider a 2s orbital, there is some distance in between where it is quite possible that the electron may not exist. There is some distance or some space here, and that space is otherwise also known as a node. So electron would be found more in this particular space and less near these two, between these two. So as the number of orbitals goes on increasing, like from 1s to 2s to 3s, we can see that in case of 3s orbitals there are two nodes here. One is after 1s orbital and the one is after 2s orbital. So it so happens as the number of this principal quantum number is going on increasing, the number of nodes will also go on increasing. Now, right now let us remember, in case of 1s orbital there is no node. In case of 2s orbital there is one node. In case of 3 there are two nodes. Now node is a point where the sign also changes from plus to minus. Previously I told you, in this case there are no nodes. So here what is happening, if we indicate this as positive and this as negative, so there is a changeover when we plot this r and r psi versus the radius. So what happens, there is a change from plus to minus, so there is one node here. Whereas in this case here there is one plus and one minus. From minus again it changes to plus. So in case of 3s orbitals there are two nodes, as we have seen here. There are two nodes here. Likewise, we can always say how many nodes are there in every orbital. In case of 2p orbitals, there are no nodes. Okay. Now 1s orbital, the probability of 1s electron, finding the 1s electron, it is maximum near the nucleus, and as the distance goes on increasing, it also decreases. As the distance goes on increasing, the probability of finding the electron also goes on decreasing. That means in 1s electron is mostly found near the nucleus. Now when you come to the 2s orbital, the probability is maximum near the nucleus once again, and then goes on decreasing as the distance goes on increasing. Now the radial distribution functions for all orbitals are the number of radial spherical nodes, which I told you just now. It can be given by n minus L minus 1, where L is the azimuthal quantum number and n is the principal quantum number. And next is the angular distribution functions of all the orbitals. They have L number of, how many? L number of nodal surfaces, are what we call as nodal planes. We don't come across nodal planes in case of s orbitals. It is seen only in case of p orbitals. Thank you.